So, have you ever been scrolling through your Amazon app and something catches your eye? Maybe it's a new pair of loafers, maybe a potted plant, or even perhaps some Pokemon cards. And you look at those loafers, those plant, or the Pokemon cards, and you think, I need this now. So, what you do is you click on it, and you click on the little button at the bottom that says same day delivery. And you have to pay an extra fee. And yes, it might break the bank, but at least you get your item fast. So, after ordering the Pokemon cards, 6 hours later, you have the Pokemon cards in your hands. Now, here, this guy, call him Ninja, he is very confused about how he got his Pokemon cards so quick. Because there's millions of people in the US and there are millions of packages. So how did his order already come 6 hours after? And today we're going to be answering Mr. Low Taper Fade's big question. How is this even possible? And this is through Amazon's science of same-day delivery. So we're going to be going into optimal transport theory. So let's envision a simpler scenario where we have a two-dimensional city with 3 warehouses and then 3 demand centers. And what we want to do is we want to minimize the costs, the transportation costs, to move goods across the centers and through the warehouses. And we also want to make sure to obviously conserve fuel. So here are the measurements for the city. The measurements for the city, obviously, they're not to scale. However, these measurements are pretty close, and they will lead us to the eventual problem. So just looking at all the roadways, think about what way could possibly be the most efficient way to transport the goods. And so, don't worry, I will not leave you hanging. I will give you some numbers to work with. So, these numbers, such as 0.2 in the middle, are talking about the supply or demand of tons of food. So, the warehouse in the middle has 0.2 tons of food to give out. And it could go anywhere. It could go down, it can go west, it can go east. So that 0.2 tons can go any direction it wants. Which one is the best? And then you got to think about, what about the other demand centers and all the other supply centers? So this is what gives this problem complicated layering and also need for mathematical and computational solving. So let's go over the way you would actually want to approach this problem from a mathematical standpoint. So our goals are to minimize costs and to serve all the demand centers. Pretty simple. That's what Amazon does to make sure that they can still pay their workers low wages and still deliver things within 6 hours. So all the math pieces are going to be our cost matrix, which is going to organize all the possibilities of where we could move the goods. And the demand and storage values, which I just recently given you, are also part of it. And the transport plan and the weight is how much weight we're moving where. So that's our final plan that we're going to develop. And the way we're going to do this is using First, the cost matrix, which is to organize all the possibilities. So C sub ij, where mass moves from I to j, here is formed by a matrix, and you'll see how this matrix is formed and what it'll look like. And since we're talking about distance, that's why we have the magnitude of xi minus yj, and then raised to the p. That's the normal form of our cost matrix. And when we're talking about two dimensions, we're talking about Euclidean distance. So we're going to use p equals 2 for this demonstration. So the number one way to do this, and my favorite way, is the Kantorovich formulation. So here, it may look complicated, but it is really easy to understand. So our A in the set of Rn and B in the set of Rm, all that is doing is that is tracking how many supply and demand centers there are in the city. Are A and B being greater than or equal to 0, all that means is that the supply or demand can't be negative. You can't demand -2 oranges. And then the last part means that if you were to sum up all of the warehouses with all of the neighborhoods, they would all equal 1. So A and B form a cost matrix C that is Rnxm, and Nxm happens to be the dimensions of the cost matrix. And since we have 3 supply centers and 3 demand centers, that means we'll have a 3 by 3 matrix. So our goal right here is to minimize our transport plan with the cost matrix, and we're summing together all of the possible combinations here. And so if you want to know exactly what this formula means, let's dive right into it. So here we have gamma right here. This is the symbol we're going to be using for this video. All this is talking about the transport plan shown below to optimize where the weight goes and how much weight goes along the road into the demand centers. So all this refers to is the plan. And then for the second part, this is all just to sum all the supply and demand combinations in total. And the reason is because certain supply and demand combinations, for example, a mass of 0.2 going to somewhere that needs 0.4 costs a certain amount of money. And if you were to also do another transaction somewhere else, you need to add up all the transactions in total to get the total cost. So all the parts and all the separate routes have to add up, and that's what gives you the total cost. So the first step you want to take is using the Wasserstein 1 distance formula. And this is given by W1 of AB, which are our supply and demand parameters, is the minimum of our supply and demand plan. And what we're going to be doing is we're going to be summing over the distance and the plan to move I to J. So we have a few issues with this formula, though, because it's unstable, it's complex, and it's stupid. And it may not look stupid at first, but the thing is that this formula is pretty useless because all it knows how to do is take all of the stuff from some warehouse and move it to the next one. So there's no actual distribution of the mass. So it's just too simple, and it doesn't lead us anywhere. So what is the solution? To add more confusion and more randomness to the situation. It makes no complete sense at all. Well, it will soon. Because with the concept of entropy. So with entropy, the supply can be distributed however it wants to the demand. However, without the entropy, as discussed before, you can only move the entirety of one mass to another center. So that's why we need to add an element of entropy for it to make sense and for it to work. So this is the entropy regularized objective. And so the goal is to minimize the transport plan, the cost of it specifically. And we added a component of entropy where epsilon is the smoothness of our delivery. And this sum part is just a logarithmic based reward for being random or distributing the supply. So now with this information, what we're going to do is we're going to use something called the Sinkhorn algorithm. And what this is going to do is this is going to look at our cost matrix for our values that we were given, and it is going to iterate itself a few times. And after it iterates itself a few times, then it will show us how everything works and what is the optimal plan. So after iteration 0, or during iteration 0, we have a lot of dark colors. Dark colors in this case mean more expensive, and light colors means cheap or cheaper. And so for iteration 0, there's a significant amount of very expensive things that we could easily clean up. Now let's look at iteration 1. Iteration 1, we've got rid of some of the darker colors. They're still present, and some of the colors have lightened up. But we need to run this algorithm a few more times for it to actually minimize the costs. So here we see a pretty major change here in iteration 3 to have to do with the cost. There's only a few dark squares now, and there's all the ones that are very white, or at least baby blue looking. So now let's look at iteration 3. And iteration 3, we have a lot of baby blue, and we have very little dark going on. And then after iteration 4, we have a completely baby blue, fully minimized algorithm here, cost matrix. So if we look inside this cost matrix and what a computer program or the computers over at Amazon are doing, because I obviously ran a Python code to figure out these values. So here is the Gibbs kernel matrix. The Gibbs kernel matrix, all this is showing us is that there's a negative exponential correlation between the cost and the plan. Essentially, in other words, this is showing us that through the Sinkhorn algorithm, it's going to start out to be very expensive. However, the cost is going to decay over time, as shown in the animation that we saw before. It only took 4 iterations for it to be completely minimized. Of course, the exact amount of iterations it took isn't very important because you can just run it in a program like Python. But what is important is to understand that due to the Singhorn algorithm, it will get better each time you run the iteration. All we need to do to solve this problem is to input our data vectors. So this is basically just saying how much supply and how much demand is where. Let's just say that that U, for example, is the supply and V is the demand. And so it's listing all of the areas with demand. So in this case for supply, there's a warehouse with 0.2 and then there's 2 warehouses with 0.4. So a possible vector could be 0.2, 0.4, 0.4. And same thing for the demand. So after we input everything, we get that this is the optimal transport plan for this fictional city, where this middle warehouse transports 0.2 tons of food to the top left neighborhood. The bottom left warehouse transports 0.1 tons to the top left neighborhood. The warehouse on the bottom left also transports 0.3 tons of food to the neighborhood in the middle. And then the warehouse in the bottom right transfers all 0.4 tons of food to the demand center that's right next to it. So in total, after running this through Python, running the algorithm, you get that the cost matrix will turn out to be 11.83. So $11.83 is how much it actually costs for someone to deliver all of this food. So how is this applied at Amazon? Well, at Amazon, Mr. Jeff Bezos over here, he has a lot of money and he can afford computers for him to do very complex math such as this on a very large scale. For example, if you look on the right, we have the city of Los Angeles, very complicated city. There's a lot of paths, a lot of roads, and also you have to consider other factors like traffic and certain weather conditions or whether roads are closed. So all of this super complex math makes this problem even more complicated. And so Jeff Bezos has to get supercomputers to do math for him to minimize the costs to actually transport the goods. And this is how he invested in these supercomputers, and this is how he stays rich while you all are scared of the $11 fee. Anyway, I hope you enjoyed this short little essay. Fun video to make. Took a long time. I would appreciate if you would subscribe and like the video. Comment to let me know that you made it this far. And I'll see you all next time. Goodbye.